So, ladies and gentlemen, good morning and welcome to today's training. Today we are beginning with IP multicast basics. Multicast is a term that I'm sure is not very new to you. At the very beginning, when we were doing HCI, the very first topics, we talked of type of messages that can traverse the network. So we talked of unicast. What else did we talk about? We talked of broadcast. We also mentioned multicast. And later on, when we were learning about IPv6, we also mentioned something to do with anycast. So these are just type of messages. So when you talk of unicast, we're talking of one-to-one. So a one-to-one packet will have a source, a specific source IP address, and a specific destination IP address. Then this one is one-to-all. So it will have a unicast source address specifying that particular source. Am I spelling one correctly, by the way? Is this how one is spelled, by the way? 1, 2.
Yes.
Okay. So we also have one-to-all. So one-to-all, we are talking of you have a single source and the packet is supposed to be processed by everyone. So you have a broadcast destination address. Then we had multicast. Multicast is one to a group. So the source address of a multicast packet is a single IP, unicast IP address, but the destination address of the packet is a multicast address that is supposed to be processed by a group. So far, we've met several multicast usages. For example, that particular multicast address that is used to identify all routers in a network. So when you just want to send a packet that will be processed by routers only in your network, that will be the destination multicast address. Then when we were learning about IPv6, we learned about the anycast. And we saw that in anycast, you can have many sources and many receivers. So it's almost like many to many. So if, for example, we are talking of YouTube servers, you have YouTube servers hosted at each continent, for example. And therefore, if a receiver wants to watch a YouTube video, all those servers in each continent have the same image. They have the same everything. So if someone wants to watch a video from Kenya, then they're going to be redirected to the YouTube server hosted on the African continent. So that is what we call anycast. You can have many servers being referred to with the same IP address, and now it is the IGP that is going to determine the server that is closest to you. So that is what we call anycast. So in the 3 topics that you're going to look at this morning, we're going to focus on multicast. So we want to understand deeply how multicast works and also some of the applications of multicast packets. So I'll read the forward. If unicast technology is used for point-to-multipoint communication. So point-to-multipoint. So you have a single source, but many receivers, point-to-multipoint communication. Now, the amount of data transmitted on the network will be proportional to the number of users that require that data. So sending multiple copies of identical data on different users wastes resources on the data source and also on the network bandwidth. Now, if broadcast technology is used, as we are going to see, hosts that do not require the data will receive the data. So in point-to-multipoint scenarios, if you use broadcast technology, so you're simply sending to everyone, some hosts do not require that data, but they're still going to receive it. Now, this threatens information security and causes storms on the local network segment. Now, the solution is IP multicast. So IP multicast technology resolves the preceding problems. The multicast source sends only one copy. So the multicast source sends only one copy of data, which is then replicated and forwarded by network nodes. Finally, sent to only specified receivers. So that's how multicast, this is just a very wide summary of how multicast works. So we have a single source, sends a single copy of data. Then the data is replicated as is being forwarded towards the receivers by what we call network nodes, which are simply routers. Then they are finally sent to specified receivers. So this whole scenario of IP multicast technology is what we ought to understand in this topic. So by the end of this chapter, we should be able to. Solomon, please help us read out these objectives. Okay, John?
Be familiar with characteristics of point-to-multipoint applications. Master the basic multicast architecture.
Yes.
Understand the structure of multicast addresses.
Very well. Okay, so let's begin with the characteristics of point-to-multipoint application development and deployment. Okay, so traditional point-to-point applications. Now, a service provider delivers services on a per user basis. So the service provider transmits different data to different users. Some of these applications on the internet include email, web pages, online banking, and so on and so forth. So really, most of the time, they are deployed using the client-server architecture. So you have a server, then on the internet, you have clients. Now, whenever each client makes a request to the server, a copy of that particular file, for example, your bank statement, is sent to you as an individual. So what really this means is that there's a specific destination IP address for reaching client B, and multiple copies, personalized copies of the data is actually sent from the servers to each of the clients. Now, of course, we already understand that on the internet, the packets are sent hop by hop from one router to another router based on the routing protocols that have been configured on the path towards the destination. Okay. Now, new point-to-multipoint applications have actually emerged over the years, and they have become common. For example, what we are using right now to learn, video conferencing. With the pandemic, many people have gone into that. We also have web TV and online live broadcasting, like most of our local medias have channels where they go live. They broadcast live maybe some part of their programs like the news and so on and so forth. So really, when it comes to point-to-multipoint applications, a service provider delivers services based on groups of users. Because right now, I'm the service provider and I'm delivering this particular tutorial to you, and you guys are a group. And only those people that have paid for this training have actually joined this particular group. So with point-to-multipoint, it's one to a group. Now the service provider transmits identical data to all users in the same group. So all of you are getting the same thing that I'm speaking about here. So really, that is what we call a point-to-multipoint. Now, a point-to-multipoint scenario requires high information security. Because, for example, for web TV and even video conferencing, you only want those people that are legit and are supposed to attend the video conferencing session to be able to attend. So that's one of the requirements for point-to-multipoint. It also requires wide transmission scope. So for example, web TV, like we have DSTV, they also have a web page where if you've subscribed, you can be able to, if you've paid for that subscription, you can be able to watch all their programs through the web, so you don't need a dish. So you see, it really requires a wide scope of transmission, and it also requires high bandwidth. Sorry. So those are some of the requirements for implementing point-to-multipoint scenarios. Okay, so let's see. What happens if you deploy point-to-multipoint applications in unicast mode? What happens? So what that means is this: we have the finals. And DSTV is broadcasting the finals, and their viewers, their subscribed viewers all over the world, want to watch the match via the web. So if we are transmitting these packets in unicast mode, what that means is that we send a specific stream to each individual, to each subscriber. So those ones that have not subscribed are not going to receive anything. But actually, we send a unique packet, a unique stream to each of the receivers. Now, these will cause a lot of problems. One of them being, we're going to have too much duplicate traffic on the internet, as you can see from the red lines there. Number two, many device and also link bandwidth resources are going to be consumed. So for the routers, imagine processing all this. So we're going to have congestion. And delays. And the service here is not going to be good because the videos are going to keep hanging. And if you've actually tried watching a match through one of the Paradoi servers, that maybe use unicast mode in transmitting these particular matches, you see that most of the time it keeps on hanging. Then it's also unable to ensure transmission quality. of course, because of these challenges like congestion and so on and so forth. Okay. Now, the other alternative is that you can also try and deploy point-to-multipoint applications in broadcast mode. So in broadcast mode is like this. So you have the match in your server and you want to send to everyone. So you simply send a single copy. You send a single copy. When it gets here, then like that. So we don't have a lot of traffic on the network, but again, these has problems. So the first problem is it has limited application scope. And the reason as to why it has limited application scope is because even non-receivers are going to receive those packets. That is number one. Number two, you can only send broadcast packets in a local area network within the same network segment. So as you know, broadcast packets cannot be routed beyond the network segment from which it was generated. So that's why its application is limited within a single network segment. The other one is it's also unable to ensure security because even non-receivers receive the packet in the network. And it's also unable to charge for services. So most of these point-to-multipoint applications, they require users to subscribe for and pay for services. So how do you implement that if non-receivers can also receive that particular packet? So that's the problem with implementing point-to-multipoint applications in broadcast mode. Those are some of the challenges that it will face. And now the solution to this is multicast. So point-to-multipoint applications should be implemented in multicast mode. So when multicast transmission is implemented between a source and multiple receivers, then we have a single stream of data, all the way from the source to the receivers. So we have a single copy. So this ensures, for example, that bandwidth and CPU resources is conserved. So we do not have duplicate traffic when we use the multicast mode. It also ensures high security, as we are going to see the implementation. So in multicast mode, non-receivers are not going to receive this particular packet, as we are going to see in the implementation. So for example, here we have 4 receivers and 3 non-receivers. So we are going to understand how really it's implemented. And therefore, because non-receivers will not be able to receive the packet, then it can ensure that only subscribers and people who have paid for the service can be able to access that particular service, thereby guaranteeing the service provider's business return. So really, multicast packets from the source to the receiver follow, they actually are transmitted via a path which is normally called a multicast distribution tree. A multicast distribution tree. So you see the path looks almost like a tree, if you can look at it from here. Like a tree. So it's called a multicast distribution tree. And we are going to look at 2 types of trees one of them called SPT and another one called RTP, that actually enable multicast distribution of packets. Okay, so once we've understood the solution to point-to-multipoint application, now let's go on and look at multicasts. So the multicast overview. So the basic architecture is very simple, simply made up of three, do I call them layers? 3 layers. So the very first layer is the interconnection between the source and the gateway. So the very first router that is interconnecting the source to the internet. Then the other one, not necessarily the internet, by the way. Then the other one is now router to router. So how the packet flows across the network or the internet from router to router. So that's the second layer. And the very last layer is that last router that interconnects the receivers. So it's known as router to receiver, router to receiver. So in general, that is the basic multicast architecture. So generally, the source will send to the gateway, then the gateway will send to a router, and the router will share the data until it gets to the very last router that now has the clients that need to receive that multicast data. So the client receives the multicast data. The routers responsible for multicast data forwarding. Then the source is responsible for the multicast data generation. So that is it. Now, we know that for unicast packets, we specify a unicast destination IP address. We also specify a unicast destination MAC address. So how does a multicast source encapsulate multicast data? So how does the source, when it's generating the multicast data and wants to send it to the gateway, how does it encapsulate it? In particular, we are interested in what will be the destination. What will be the destination IP address of the multicast data? And what will be the destination MAC address of the data? Because for the source IP address, it is simply the IP address of the source. And for the source MAC address, it is the MAC address of that particular interface on the source. But what of the destination? What of the destination? Now, generally, the multicast packets are actually encapsulated using multicast IP addresses and also using multicast MAC addresses. So we are going to see how. So this is what is going to be the destination MAC address, and on the destination IP address field, then we are going to have a multicast IP address. So let's look into the multicast IP address here. So if you can remember, which class in IPv4 address ranges was reserved for multicast address range? Anyone? Class what? Yes, it begins from 224 .0.0 all the way to 239, the whole of it. So which class of IP address is this? Is it class A, class B, class C, class D? Which one? Anyone?
Class E.
Class E, actually. E for experimental. E for experimental. Otherwise, for multicast, it is class D. Class D. And it ranges from 224.0.0.0 to 239.255.255.255. Now, a multicast IP address represents a group of hosts, but not a specific host. So if a host joins a multicast group, it means that the host wants to receive data packets destined for the multicast IP address. So you can think of it as joining a WhatsApp group. If you're not in a WhatsApp group, you're not going to receive a message that is sent to that group. Now, generally, multicast IP addresses have been divided into different ranges for specific purposes. So, for example, 224.0.0 all the way to 224.0.0.255. So all that address range from .0 to .255 is reserved for routing protocols. We've already seen .5 for all routers, .6 for all DR others, and so on and so forth. .5 for DR routers, .6 for all DR others routers. So they are reserved for routing protocols. Then we have this range that is reserved for what we call any source temporary group address. Then you have this one reserved for source specific temporary group address. Then you have this one that is any source group address. Any source, but can only be used within private networks, private multicast domains. Okay, now, okay, it's even here. We have two models. We have two models that are used to deliver multicast packets. One of them is known as ASM, any source multicast. Any source multicast. Then the other one is known as source specific multicast model. Now, the main difference between ASM and SSM is as the name suggests. So with any source, the receiver does not know who the source is and does not specify who the source is supposed to be. So you see, we might have several servers which might act as the source of a multicast packet. So maybe you have server A, server B, server C, server D. So if we have a receiver here with any source multicast, they do not know where these servers are, and they cannot specify that they want to receive packets from a particular source. On the other hand, with a source-specific multicast, this guy can explicitly decline multicast packets from the other sources and specify that they want to receive multicast packets for that particular source. So that's the difference between any source multicast and source-specific multicast. Now, just like just like you can do with WhatsApp, you can actually join a group. So when you talk about group here, we're actually talking of a multicast group. So you can join a multicast group, and you can also leave a multicast group. So when you join a group, you receive packets that are destined for that group. When you leave the group, you don't receive packets from that multicast group. Okay. So we now look at the multicast address. So we've just looked at the multicast IP address. Now we look at the multicast MAC address. Now we know that, for example, in unicast communication, we have to include a destination MAC address. And in unicast communication, how do we learn the MAC address of the destination? Because initially we do not have the MAC address of the destination. So how do we learn in unicast communication? How do we learn? Using what protocol? Anyone? Hint, it starts with an A. Anyone?
ARP.
Exactly. So in unicast scenarios, we use ARP to learn the MAC address. So what about in multicast scenarios? How do we go about it? Now, when we were learning about the MAC address, we said it's made up of 48 bits, normally written in hexadecimal in those parts. And we said also that the high order bit, no, the last bit of the first octet, let me use this one instead of using high order. The last bit of the first octet is a 1, if that MAC address is a multicast MAC address. Otherwise, if it's a unicast MAC address, then the last bit of the first octet is usually a 0. So that's one of the main differences between a unicast and a multicast MAC address. Now, IANA. IANA specifies that the most significant 24 bits of an IPv4 multicast address are, and the 25th bit is always a 0. So what really this means is that for any multicast address, it will always begin with those values. So 0, 0, 1, 0, 0, 5, E. And the 25th bit will always be a 0. So that means that the first 25 bits are actually predefined. So what does that leave us with? We know that they're supposed to be 48 bits. So if we do 48 minus 25, what do we get? 23 bits. So for a multicast MAC address, the first 25 are reserved. So what can vary is the last 23 bits. So now in the next slide here, we look at how we generate a multicast MAC address. Generally, we generate a multicast MAC address by mapping a multicast IP address and a multicast MAC address, under MAC address, under multicast MAC address. So how do we do that? So as I've just shown you, the least significant 23 bits of a MAC address, the least 23 bits of a MAC address. So the least significant 23 bits. So the most significant 25 bits, tumeona itakuanga tu hivyo. It will always be like this. So the remaining 23 bits are actually mapped to the least significant 23 bits of the multicast IP address. So we simply take the last 23 bits of the multicast IP address and use it. We map it, and therefore what we come up with is a multicast MAC address that is unique. So that is how multicast MAC addresses are actually generated. That is how multicast MAC addresses are generated. Okay. Now, this can cause a problem. This can cause a problem because, as we know, so problems caused by address mapping. In multicast IP to MAC address mapping, 32 multicast IP addresses are mapped to one multicast MAC address. So this is an IP address. An IP address has 32 bits, and we know that a multicast address has to begin with 224 dot blah blah blah. So 224 will always begin with 111110. So it will always begin with that. Then we are taking the last 23 bits. So we are going to map these last 23 bits to the MAC address. Now, what that implies is that we are left with 5 bits. Now, if we do 2 raised to power, if we do, where is raised here? If we do 2 raised to power 5, we actually get 32. So that means that only that 32, we only have 32 multicast IP addresses that can actually be mapped to the same 32, because these can differ 32 times, 32 times. So it means that 32 multicast IP addresses can be mapped to the same MAC address. 32 MAC address. So it's important to understand that 32 multicast IP addresses, there's a probability that they can be mapped to one multicast address. However, the engineers of this particular mapping, who are actually IETF, say that the probability is low for you to have such like a scenario in the same LAN where any multicast IP address is actually mapped to the same MAC address. And therefore, this problem generally is ignored. It has not been solved, but it's simply ignored with that in mind, that the probability of it occurring in a single network segment is actually low. So generally, that is the basic about IPv4 multicast communication. So we have 2 questions here. What is IPv4 multicast communication, and what is the range of IPv4 multicast addresses? I want you to look at that as I open up the next chapter. Any question, by the way? Any question? Okay, asanteni sana.